So this video is I'm going to be talking about the Fermi-Dirac integral. And specifically, it's in reference to semiconductors, where it comes into calculating the total number of electrons or holes that can exist in an excited state. And so really this starts off by first knowing your density of states. You get this from the EK diagram we've talked about in a separate lecture. And this is defined down here in terms of the effective mass, so the curvature of the density of states. The curvature of the EK diagram. Here we're looking at the valence band edge and conduction band edge, and these are an increase in density of states. Now, we've also talked about the Fermi function, which is shown here. So the Fermi function is the occupation probability for electrons to exist in discrete states. And we derive this specifically for electrons using Fermi-Dirac statistics. And it's shown here, here we have a Fermi level, which is in the middle of the gap. And so far away from the Fermi level, the occupation probability gets low. And what you would do for electrons, for example, is multiply the density of states by the occupation probability, and then you get a carrier distribution. You can do the same thing for holes, one minus the Fermi function though. Okay, so we get this distribution of electrons and holes, and it's bunched up near the band edge, which is nice because this is where we've made some assumptions. And now instead of looking at the carrier distribution, which is drawn here in terms of inverse volume, so per cubic centimeter EV, what we want to do is know the total number of electrons. Okay, so this would be, for example, electrons or holes distributed in energy. And what we want to know is so let's compute the equilibrium carrier concentrations, okay? So how do we use this distribution and get an equilibrium concentration? And so for that, let's integrate this. Let's look at for electrons specifically. So electrons, we take the integral from the edge of the conduction band to the top of the conduction band, and we multiply the density of states by the occupation probability. Those functions are rewritten here for convenience. And what you'll see is that we get the number of electrons is equal to the effective mass of electrons times the square root of 2 times the effective mass of electrons over pi squared h bar cubed. Okay, that's everything written in here. Let's pull the energy inside of the integral. So we're going to integrate from the bottom of the conduction band, and let's make a simplification. We'll just integrate to infinity. And that's because we are mostly lumped up near the conduction band edge is where this density of electrons exist. And so if we just look at this, we can make an easy assumption that this goes out to infinity, the top of the band, because essentially the Fermi function will go to 0 this far away. Now, we bring the square root of the energy inside the integral, so we'll get E minus EC to the 1/2 over E to the E minus EF. This is from the Fermi function over KT plus 1. And this is integrated over all energy. Now, let's rewrite this, and you're going to see why at the end. But we're going to rewrite it first. Let's pull the effective mass out. Okay, so we get effective mass, and let's do 2 to the 1/2. I'm going to leave some space. So the effective mass we're going to pull out. So this would be to the 3/2. And we're going to divide by pi squared h bar cubed. Now we're going to integrate from EC to infinity. And now let's divide by KT to the 1/2. So we have E minus EC over KT to the 1/2. So that means we need to multiply by KT to the 1/2 to get the same value. Okay, so we're going to divide and multiply by KT to the 1/2. And then let's take the Fermi function, and we'll say E, we need to rewrite this. And we can rewrite this in terms of a conduction band by saying E minus EC over KT. And this is going to be minus EF minus EC over KT. And what you'll see is that the conduction band will cancel out, and you'll get E minus EF, which is exactly what we want. So this is the same way, it's just rewritten. let's integrate over all energies. Now, we can rewrite this as our effective mass of electrons to the 3/2, 2kT to the 1/2 over pi squared h bar cubed, integral from the conduction band edge to infinity. And now let's say epsilon to the 1/2 divided by e to the epsilon minus eta c plus 1. And this is going to be the integral over energy, so dE. So the reason we separated this out was so that this term on top matches this term in here, and we can rewrite it as epsilon, okay? And so we've got epsilon, which is defined as E minus EC over KT. And we've got eta C, which is going to be EF minus EC over KT. So the next thing we want to do is replace this integral to be an integral over epsilon instead of an integral over E. So let's look at epsilon. So what you see is that d epsilon equals dE over KT, or dE equals KT d epsilon. And so we can rewrite En is going to be, let's say, effective mass of electrons to the 3/2. Now, let's look at what would happen when we replace dE with KT dE. We're going to get an extra KT, so let's pull that out front. So we have KT to the 1/2 times KT to the 3/2, okay? Or KT to the 1/2 times KT. We'll give you KT to the 3/2 so we can pull it inside of the 3/2. And then we're left with just 2 now to the 1/2 divided by pi squared h bar cubed. And now we have the integral. Now, if we integrate from EC to infinity over E, this will be the same as integrating from 0 to infinity in epsilon, okay? So epsilon to the 1/2 divided by E to the epsilon minus eta C plus 1 d epsilon. Now we're going to do another really strange thing, and that's going to be rewriting this prefactor. So we're not going to do anything, but we want to pull out a term. We want to pull out a 2 over square root of pi, because this is going to help us to define something on the next page. So let's pull out a 2 over square root of pi. We'll rearrange it. And so here we're going to take the effective mass of electrons, KT to the 3/2 times 2 to the 1/2. And let's first take this h bar, which is h bar is the reduced Planck's constant equals h over 2 pi. So we're going to say pi squared h cubed over 2 pi cubed to get rid of the reduced Planck's constant. And so this is going to be 2. Now we have 2 cubed times 2 to the 1/2. This would be 2 to the 7/2. Okay. So let's pull one of those into the 3/2. And then we have 4 more. And you're basically going to get 2 cubed times 2 mn effective mass KT to the 3/2. Okay, so this is going to be 2 to the 7/2, which is what's going to be from these terms. And the pi cubed is going to cancel out with pi squared to just give us pi on top. And this is going to be divided by h cubed. Now we're going to multiply by pi to the 1/2 over pi to the 1/2 to give us 2 times 2 pi. So we'll bring a pi to the 3/2 in. Effective mass of electrons, KT over h squared. So we're going to bring, this is pi, we're going to bring this pi to the 3/2 in here. And then we're going to bring h bar cubed into the 3/2 as well. So this is going to be 1 over h bar squared. And then we're left with just this 1 over pi on bottom and the extra 2 that we had here. Okay, so we pulled out one of the 2's. So basically we'll get a 2 over square root of pi. Okay, so this is how you can rewrite the prefactor to get a 2 over square root of pi out front. Seems arbitrary and bizarre, but it's going to make sense in a second. So this is our equation, right? We have this electron density in terms of an integral. And this is a very special integral called the Fermi-Dirac integral, okay? And this it's going to be to the order 1/2 in this particular case. And we can rewrite this then in terms of the effective density of states, okay? So this is going to be this term here, the effective density of states. And then we have a 2 over square root of pi times, we'll do capital F subscript 1/2 eta c. This is going to be the way we can write Fermi-Dirac integral order 1/2. The subscript indicates the order, okay? So this is going to be where, let's just copy these over. And this is going to be the definition of, well, we don't need eta. We don't need epsilon. We need eta c. And then we have this in c, the effective density of states, which is just going to be this term here. And this is how we define the effective density of states after pulling out this 2 over square root of pi. Now, these terms together, 2 over square root of pi and the Fermi-Dirac integral, are something that we would call the modified Fermi-Dirac integral, okay? And this is commonly what you'll see. I'll do this curly Q F eta c. So this incorporates both of these terms. We'll say this is the modified, okay? And so a general form of the electron carrier density is going to be effective density of states in the conduction band times the modified Fermi-Dirac integral order 1/2 eta c. Okay, and this is actually a really nice way to write it. And generally you don't see it this way. Generally you see an exponential, but this is the full definition for any value of the Fermi function. And you can do the same thing for holes, but you do the valence band density of states and eta v, for example, for the effective mass of, for the effective mass and for the Fermi level relative to the valence band. So we can, well, I'll give you those equations at the end, but let's just look at the electrons. And now I want to tell you a little more about this Fermi-Dirac integral. So this is about the Fermi-Dirac integral, okay? So the general definition for the Fermi-Dirac integral is written like this, okay? This is a modified Fermi-Dirac. I'll just write modified. Usually they don't distinguish between the two. So they just say Fermi-Dirac and they mean modified. So the Fermi-Dirac integral subscript j is going to equal 1 over gamma function j plus 1 times the integral from 0 to infinity, epsilon to the j over e to the epsilon minus x plus 1 d epsilon. Okay, so this is the gamma function as a function of x. So for a 3D semiconductor, j equals 1/2. So this is why we call it order 1/2. And in general, j is defined for the Fermi-Dirac integral, to be greater than -1. So as long as your order is greater than -1, this integral is defined. And this gamma is the Euler gamma function. Okay, so to give you a little bit about this, the Euler gamma function is gamma of z, for example, equals the integral from 0 to infinity, x to the z minus 1, e to the minus x dx. Okay, so that's the Euler gamma function. And it's actually a really interesting function. And maybe I can show you what it looks like. Okay, so to give you an idea of what this gamma function looks like, it's generally defined, this is just from the Wikipedia page, for positive values, but it's undefined for negative integer values. But anyway, it's a really interesting function, and this forms the prefactor of the Fermi-Dirac integral. Okay, and let's look at different values of this gamma function. So we'll say for j and for 1 over the gamma function j plus 1, which is what we care about in the Fermi-Dirac integral. So we'll plot it for various values of j. And We'll just draw this dashed line, and we'll say, okay, first for j equals minus 1/2, order 1/2, minus 1/2, 1/2, 2, and order 3/2. You can get an idea. So for order 1/2, the 1 over the gamma function of 3/2, because it's j plus 1, equals 1 over square root of pi. For 1, it equals 0. For order 1/2, it's 2 over square root of pi. For order 2, it's 1. For order 3/2 is 4 over 3 square root of pi. So this is where the 2 over square root of pi comes from. So we wanted to pull a 2 over square root of pi outside of the Fermi-Dirac integral because this is how we can define the modified Fermi-Dirac integral. Now this depends on the order. We already knew it was order 1/2, so we knew we wanted to pull out a 2 over square root of pi from the effective density of states. We can separate them. If it was order minus 1/2 or order 1 or order 2, we would want to pull out a different prefactor from the effective density of states. And in general, you don't have to have a 3D semiconductor. You could have a 2D or a 1D semiconductor, and your order for the Fermi-Dirac integral will change. So you need to understand your order first, and then you can know your prefactor to pull out so that you can compute the effective density of states. And so in this case, we know the order. It comes from the gamma function, 2 over square root of pi. So I'm just going to write this. This is where 2 over square root of pi times the Fermi-Dirac integral equals the modified Fermi-Dirac integral comes from. It comes from the 1 over the gamma function. So this is why we pulled it out. Now, a better question. Can we plot this? Can we actually compute it? Do we have to just look at plots in a book? And yes, we can plot it. The challenge is there are no Fermi-Dirac integrals in Python, okay? So what we're going to do is we're going to do this in Python, but we need to define the Fermi-Dirac integral in terms of another function, okay? So you can actually look this up. For example, go to the complete Fermi-Dirac page on Wikipedia. You can see this is the definition of the Fermi-Dirac function. And on the second line, you can see here, this is the Fermi-Dirac expressed in terms of a function called the Pauli logarithm, okay? So the Fermi-Dirac integral can be defined in terms of the Pauli logarithm. So let's write this definition out. So the Fermi-Dirac equals minus, let me write it in black, minus Li subscript j plus 1. So this is going to be 1 order greater than the Fermi-Dirac function. Evaluate at minus e to the x. Okay, this is a Fermi-Dirac integral of x. This is called the Pauli logarithm. Okay? And so for absolute value of negative e to the x less than 1, this is going to be defined for a real number. So x less than, basically this thing, x less than 0 is going to be how you get for a real solution. And if x is greater than 0, you're going to get a complex solution, okay? And so we can rewrite our electron density. N equals the negative effective density of states, Li to the 3/2, okay, because it's Fermi-Dirac integral 1/2. So 1/2 plus 1 is 3/2, minus e to the eta c, or if you want to rewrite this in terms of exponential Fermi function, minus effective density of states, Li to the 3/2, minus e to the ef minus ec over kt. Now we have to be careful that Li is written for a bunch of things, of log integrals. Make sure we're using the Pauli logarithm. That's the function that it's defined for, okay? So, yeah, this is the Pauli logarithm. You can take a look at this. Pauli logarithm is kind of interesting. It's got these really, I mean, maybe they're just interesting on a colorful plot, but it's got this really interesting shape and behavior depending on the order of the Pauli logarithm. So this is the function we want to use because they're built into Python. So we can use the Pauli logarithm. And let's be clear that this is defined for these values of eta and the effective density of state. So this is what those correspond to. And what do these bounds limit? Okay, so if x is less than 0, we can take a look at an energy band diagram. So if this is going to be our conduction band and this is going to be our valence band, there's going to be some Fermi function, and it can be somewhere in the gap in this case. So if the Fermi function is in, I'll just say the band gap, e.g., what you get is a negative value for eta, because this is eta x less than 0, and this would be for eta less than 0, meaning the Fermi level is less than the conduction band edge. So this is for the Fermi level within the band gap. You get band gap, you get a real solution. You can also evaluate the real part of the polylogarithm when the Fermi level is above the conduction band. This is really degenerate semiconductor. If you have a lot of electrons, you can look at the real part of this solution, but know that it's complex once you go above, the Fermi level goes above the conduction band, or an arbitrary level you're looking to solve for. Okay, so let's take a look at how these solutions can be plotted in Python. And so this is our script. We can start with having NumPy and Matplotlib, because we're going to plot these things, and let's define our constants. Okay, so we want to define our effective density or effective mass. So we're going to say this is 1 for electrons. We need to know our electron mass, which is 9.109 E minus 31 kilograms. H, not H bar, we're using H as Planck's constant, 6.626 E minus 34, and this is going to be in units of joules times seconds. We have Q, which is going to be 1.602 E minus 19, and this is how we're going to convert EV to joules. And we have KT, which is going to be 0.026. So you can just remember at room temperature, this is 26 MeV, okay? EV at 300K. So we just do these generally at room temperature. And now we want to know our effective density of states. So our effective density of states in C is going to be, if you look back at this equation we just derived, I'll just type it here. It's 2 times pi, so you do NP pi, times the effective mass, so M star. Now this is the reduced effective mass, right? So this is a relative effective mass. So we're going to do M star times M naught. This will give us the effective mass times KT divided by H squared, and all of this to the 3/2. And then this will be in SI units. You can check this will be in meters. So we're going to multiply by 100 to the minus 3 to give us units of centimeters to the minus 3, okay? Now we want to define our energy space. So we take our energy space and let's say EF minus EC is what we're going to define this for. So how far is the Fermi level below the conduction band? This will be a negative value when it's in the gap. So we can use NumPy lens space, and let's go from minus 0.25, so 250 millielectron volts below the conduction band to at the conduction band, and we can do it in 100 steps. Okay, so this is in units of EV, we'll call it. And now let's evaluate our function. So we have to do a for loop, okay? For this, we're going to use a special function called MP math, okay? So we want our special library called import MP math, and we're going to import it as MP. And this is where the the polylogarithm is defined, and you can't pass a list of values, so we're going to do a for loop. So let's initialize the list. Our list, our Fermi-Dirac list, is going to be blank to start off with. And then we're going to say for I in EF EC. Okay, so for every energy value in this list we made, let's pass it that value. And we'll say the Fermi-Dirac, evaluated Fermi-Dirac is going to be MP polylog, okay? MP.polylog. This is the polylogarithm. And if you look it up, it takes 2 arguments. It takes the order and then it takes the value. And so for us, it's going to be order 3 halves, okay? Or in our case, it's the order of the Fermi-Dirac integral, which is 0.5 plus 1, j plus 1, so 1/2 plus 1. And let's put this in parentheses just in case here, but I don't think this should matter. And then now we're going to say the argument. The argument is the negative exponential of your EF minus EC over KT. Okay, so I is going to be all these different values we're passing. So we're going to do I over KT, and these are all both in units of EV. Okay, and that reminds me we need to go up here because KT is in units of EV, and the Planck's constant is units of joules. Okay, so we need to multiply this by Q to convert it to EV, or to convert it to joules. But in here, both of these, I and KT, are in EV, so everything's fine. And this is going to give us a polylog, okay? And the trouble is it gives you a very complex wrapper, an MP math value. And so if you want to extract an integer from this, you need to convert it to an array, but then it'll get tricky when you have complex numbers, okay? So the first thing we want to do is take the real part, okay? So we'll say mp.re. This is how we extract the real part of this solution, so we don't have to worry about complex solutions for positive values. Just to make this general, because it can get tricky depending on how you define your list. So we want to define the real parts. And then we will take our Fermi-Dirac value, and we need to convert this to a NumPy array, okay, rather than some wrapper for MP math. And so the Fermi-Dirac we just said is defined as minus the effective density of states times this polylog. So we're going to turn into an array, a NumPy array, NP array, and then let's take FD, and let's say it's going to be D data type float. So we're going to convert the output of the polylog function, the real part, into a floating value, okay? And this is going to be fine. Now we can do normal math operations on it. And now we need to add it to the list. So we're going to take our FD list that we initialized, and we're going to say np append, and we're going to take the FD list, and we're going to append it with the value FD that we just took. So this is now going to be a NumPy value, floating point, real part of the solution. And so this should be our solution. And we can run it and make sure we don't have any errors. We do have an error. Look, this is not, we're using a minus sign. I meant to put an underscore EF EC. This is just a notation for the variable. You don't want to put a minus sign there. And now everything is okay. So, okay, so actually you can see there is a parenthesis missing here. So we'll close this. And now you can evaluate, and we have our for loop making FD list is a list of array values, and this is the output of the integral, okay? So let's plot this. So the first thing we can do is use this matplotlib. So I'll put a header, we're gonna do a plot, and we'll say plot figure 1, and we'll do DPI equals 120. And then we'll yeah, let's put the values in first. So PLT plot, and we want to do our energy values. EF minus EC is going to be notated by this variable. You can use underscores, that's fine in variable names. And let's plot it versus FD list. And let's make a label. Let's call this the Fermi-Dirac integral order 1/2, and we'll make a legend. And so we can plot this, and here's what you see. So we want to put this on a log scale. So we'll come up here and we'll do plot y scale equals, or plot y scale, and then we'll say in quote marks log. And we have essentially logarithmic behavior, okay? Just to be nice and tidy here, let's add a title. So we'll do a plot title, and we'll call this the electron concentration. And we want to add a Y label. So X label and Y label. So we'll do X label. And here you can use math LaTeX definitions. So we're going to do R before we open the parentheses. So R, and then we'll do the single parentheses. And then this is going to say it's going to be math type. And then we'll do this $sign to indicate that we're going to use some LaTeX type functions. So this will recognize E underscore F. It'll put this as an underscore for the Fermi level. We'll do a backslash or / space. This will give us a space. And then we'll do a minus sign. / space will give us a space, and then E underscore C. And then we'll close the $sign, and then you can look at what this plots. It'll be EF subscript F space minus E subscript C. Okay, so this is just a fancy way to use LaTeX definitions. You can look them up. They're called math tech or something. Look at matplotlib's library. We can do another one for plot Y label, and this is going to be very similar. We'll do R, open single quotes, and let's do a fraction now. So we need our $sign, and let's say / fraction, and we'll do 2 brackets. So inside the first bracket is going to be the top 1 over, and then it's going to be centimeters, and then the caret will give us a superscript, and then everything in the bracket will be 3. This will be everything in the superscript. And we'll close out our little $sign, and this should give us a Y label now. So this is going to be 1 over cubic centimeter. So because we've integrated over energy now. So this is the electron density per cubic centimeter. And we want to compare this, okay? So what happens is if you look at a region's far away, very negative values, this is essentially an exponential function. So let's look at what an exponential function looks like. So we'll make another list. We'll call it the exponential list. This is just going to be our effective density of states times NP exp of EF EC divided by KT, okay? So this will just be our exponential list, and we'll add it to the plot. So we'll make another plot here, and instead of FD list, we'll do EXP list, and we'll make the label for this. What is the label for this? Exponential. So this is did I not? Something like this, okay? So now we'll come, and now you can look at this plot and see there's a small deviation when you get a Fermi level close to 0, meaning the Fermi level is very close to the conduction band. And this is similar to what we talked about in a different lecture. And now you see where it comes from, and you can plot it using these polylogarithms. So if we restrict our x-axis, let's pull in our x scale, and or x limit, we need to call it, sorry. X limit, let's go from minus 0.1 to 0. And we can start to zoom in on this region. So we'll also do our plot Y limit, and we'll scale this from 1e17 to 1e20. And now you can start to see where this deviation occurs. And so what happens is we said that if you're more than 3 kt away, these are essentially the same function. And so we can plot 3 kt. And let's add this to the plot. So let's take another plot. We'll do plot. And then let's add 3 kt. So we can just directly define a x list and y list. So our x list will just make 2 points. We'll make, it should be in this case, minus 3 kt. So 3 kt below the conduction band. And this will be the same. The x point will be the same for both of these data points. And the corresponding y points, let's just take the minimum and maximum of these functions. So we'll say np min of FD list. This will make sure that the values don't go too far outside of the range that's already plotted. And we'll say np max of, np max of FD list. Okay, so it gives the min and max values of whatever shows up in this blue curve. And that'll be the min and max y values corresponding to these two x values. Let's distinguish this plot a little bit. We're going to make it dashed. So we'll do a double dash line in the little quote marks, and we'll make it gray. So we'll say color equals 0.3. These are different shades of gray depending on the value. And we'll label this as 3kt. So let's add this to the plot. And now you can see this is 3kt, about 0.078, I believe. And this is essentially where you start to, let's bring the plot down a little more. And you can see below 3kt, the exponential is basically the exact same as Fermi-Dirac. And this essentially means, and you can look in the other lecture, that this is going to be Maxwell-Boltzmann statistics for the electron distribution. And for values where the Fermi level is closer than 3kt to the conduction band edge, you can see they start to deviate. And so this is where this comes from. We can plot this now for larger values. Let's get rid of these plot limits. And let's plot for positive values. So it's going to be complex. We'll go from minus 0.25 to 0.25. Now, we only took the real part of the polylogarithm. So this is how we can plot it. And if you look at the real part, this is where you can really start to see the deviations. Okay, so if you're looking at energy values, electron or Fermi values that are above the energy value you're looking at, so the Fermi level is above your conduction band, for example, then to understand the occupation at a value much lower than the conduction or than the Fermi level, you cannot use Maxwell-Boltzmann statistics. And this has to do with Pauli's exclusion principle. How do we fill electrons into discrete states? They have to have specific quantum numbers, can't overlap. And so this is where you get this large deviation. And in general, your Fermi level is not going to be that high. And so this is why we usually look at Fermi levels within the gap. They might be slightly above the gap. And you're really going to only have a challenge or an issue when you start to get to values near the edge, okay? And you can see that it's small, okay? So, you know, for 1 EV, 0.026 is maybe right here. You're talking about a factor of 2 or 3 difference in your actual carrier concentration from the Fermi-Dirac integral compared to your exponential approximation. Your Fermi or your carrier concentration will be off by a factor of 2 or so. And this depends on the temperature and various other things. And so this is the Fermi-Dirac function, okay? And this is how we can plot it. I'll put the code in the comments below in the video. I'll also upload it. And now we can, let's take a look again at our overview. So I can turn back on the iPad. And this is going to be our summary. So the electron concentration can be represented by, well, it is by definition the modified Fermi-Dirac integral times the effective density of states, meaning the effective density of states reduced by the Fermi-Dirac integral, depending on where the Fermi level is, where the Fermi level is defined by this eta c term. This can also be expressed in terms of a polylogarithm. So these are the exact same thing. We can use this polylogarithm to plot these things. So if you want to talk about real systems, if you don't want to make an exponential approximation, which is always done in solid state physics, you want to know the real value, you can use the polylogarithm. And what we find is that if the Fermi level minus the conduction band minus the Fermi level is greater than or equal to 3kt, so you're greater than 3kt away, this can be approximated as just NC e to the minus eta c. Same thing with your hole concentration. So you can do this exact same math that we did at the beginning of the lecture. Do it for holes. And you'll see that the hole density can be defined in terms of a polylogarithm or the modified Fermi-Dirac integral. And this is just our, now EV minus EF will be the energy difference for holes, because holes have positive potential when you go down in energy, where electrons have positive potential when you go up. So they're opposite. So it's the negative sign for the energy difference. And our effective mass, or effective density of states for holes is going to be defined in terms of the effective mass of holes. And that's really the only difference. And you'll find otherwise it's the same. If EF minus EV is greater than or equal to 3kt, so your Fermi level is greater than 3kt above the valence band, then our holes are in V e to the minus eta V. And so now you have all the tools to be able to derive these things for any system. All you need to do is know your effective density of states. And we can plot our total electron hole densities